Now we're going to talk about controllers um, in this sort of classic feedback loop. Here's the process, uh, and we take the process as a given and the sensor as a given. The process has an output Y. We sense it. It might have noise on it. And R is what we want Y to be. And here's where we put the controller. We work off the difference between the R and the feedback, the sensed output, and put that into the process. And we're going to talk about how to use Root Locus to help us come up with a controller. And just sort of in the interest of time and schedule, I'm only going to consider 3 different controller types. This first one is strictly proportional. All this controller is a gain, a constant K. The second one is called ideal PD, which stands for proportional differential. It has a 0. It's technically not physically realizable, considered anyway. And then the third type is here. It's called just a lead, meaning the P is much greater than Z, or the pole is much further to the left than the 0. There's all kinds of controllers we could consider, and just like I said, in the interest of time and schedule, we're not going to try all of these. They pretty much amount to what is some kind of gain. They all have some kind of gain. It could be just a gain, but they all have some kind of gain. Then they have a pole somewhere, and 0, 1, or 2 zeros. So we're going to be pretty much limited to this P, or proportional K, this ideal PD, which is a K and one 0 rather. The lead, or extreme lead, they're both the same, but P is typically bigger. So that's 3 types out of this whole list that we're going to do. So let's try. Let's do an example. Here's our process, our plant. It has 2 poles. It is already monic numerator and monic denominator. And find a controller, G sub C, to meet certain specs. I'm not going to go through how to translate those specs into where in the complex planes do you want the pole. We did that several videos ago. But if you did that, the settling time spec says you need the poles to be left of this vertical line, to the left of this vertical line. And the peak overshoot spec says it needs to be left of these slanted lines. So over here to the left is okay as long as you're underneath these 2 slanted lines. So let's try first the simplest thing, which is just pure gain K. Constant K in here. So our root locus will be this plant. Our L of S will just be this plant, and the root locus K will be G sub C. Well, the poles are at -1 and -3. There's 2 poles, no zeros, which means the asymptotes go strictly on a vertical line, straight up and straight down, straight up and straight down, and the asymptotes will be centered at the average, which is -2. As K increases, it's always going to stay in this darker line here. That's the root locus. It's never going to get far enough over. We could satisfy the peak overshoot spec. If you pick some K that kept us within these slanted lines, but no K is going to get us to the left of this line. So strictly proportional control won't work in this case. Wouldn't it be nice if we could just move this pole on the right somewhere over here far enough to get this asymptote to the left of this vertical line here, so that we'd satisfy the settling time spec. So that's one of my two methods. I call it move the bad pole. It only works if the bad pole's in the left half plane. So we'll use this type of controller, 1, 0, 1 pole. So the overall new LMS is going to look like this. And here's what we do. We pick our 0 to cancel the pole we want to cancel. So I'm going to pick Z to be 1. That'll cancel this S plus 1. And then I pick a P to get me far enough out. I think I needed to be at minus 4.6, so I'll just round it up to 5. I need 3 and P's average to be 5. I need P to be 7. So that gives me this controller. Here's the new LFS. The S plus 1's canceled, so here's my new LFS. So with that L, here's what our new root locus would look like, these solid lines. And you can see you could pick a K that would get you where you need to be to be within the settling time spec. Let's say all you want to do is just get right at this point. Oops. Right at this point here, where the two poles join and then go straight up and straight down. That's at minus 5. So what K gets us there? And I have a video of how to calculate a K. You turn the L upside down, which in our case would just be the product of these two terms, and you replace the S with the point, minus 5. So these two magnitudes, which everything's real, so the magnitudes are just absolute values, calculates out to 4. So a K of 4 with this, we had the controller. Where was it? Here was the controller, and if the this K equals 4, you'll get right to this point here, which satisfies both specs. Okay? Is that really good enough? Let's look at steady state error. Here is our KLS, which is the forward path gain in a unity feedback system. And we had a method for calculating the steady state error in that. There's no poles at the origin, so it's a type 0. So we had a way to calculate the steady state error. I'm not going to go through this. It's in the previous video. You get to this, which says the bigger you make K, the smaller the steady state error. But if you go too big, you go up this line, and then you cross this slanted line. So you violate the peak overshoot spec. So you want to find about as big of a K as you can get without going over that line. And I did it this way. If we're going up, this asymptote is at 5 or like minus 5. Where does it hit this line? Here was a calculation. Again, previous videos. It says at 6.8. At omega D equals 6.8, which means the imaginary part of 6.8. Actually, if I had this to do over again, I would back it off just a little bit so I don't touch this line. I probably would have picked 6.5. Well, let's say our design point is minus 5 plus J 6.8. What K gets us there? We flip the L upside down again and plug in for every S the design point. Remember how to do this? Pythagorean theorem, but first you combine all the real parts and all the imaginary parts. So minus 5 plus 3 is minus 2. 2 squared plus 6.8 squared. Here I have a minus 5 plus 7, which is 2. 2 squared. Anyway, do this arithmetic. You get 50. Here is our control. And we use root locus to do it. You want to check it out after you do all that. If you do all that, Here's the overall closed loop transfer function, and it is a scaled prototype second order system. So you could calculate the terms. The settling time should be 0.8. Peak overshoot should be 9.9. Got what we respect at. We respected settling time of 0.87 and peak overshoot of 10%. So we calculated to be within spec. And when we simulated with MATLAB, peak overshoot was 9.9, that's under 10, and settling time was 0.7, which is under the 0.89. So it meets both specs. Sometimes picking the design point is a little bit of art, but I told my students, just know the science part, cranking through the numbers. We'll worry about making approximations and that kind of thing later. So that's one of two major methods. I call it the move the bat pole method. The second method I teach is I call the bend it method, and I'll save that for another video. Let's end it here. Just kind of slow here.